It's Cool. So let's start today. Uh, so today the rough agenda is going to be to uh, sort of give you this weird saying that every expander is like basically some convex combination of a complete graph and some error. And we will try to formalize exactly what we mean by this, and we will see one application of it. But this is just something that will show up in many of the applications. And in fact, one of the things I would like you to try out is like once you see this, try and reprove the expander mixing lemma using this method. And it turns out to be a rather slick proof. You might get slightly worse parameters, but it's a pretty slick proof. So, okay, so let's look at just do a brief recap so that we're all on the same page. We have been sort of purposefully looking at undirected graphs which are possibly not regular. And we were talking about the random walk matrix, which is given by D inverse times A, where A is the adjacency matrix. And there was a particular spatial distribution that was natural, which was like the distribution that's proportional to the degree at every vertex. And corresponding to that, there was a particular inner product we were looking at, which was a convenient inner product to work with. And with respect to that inner product, we could see that there's a bunch of eigenvectors with real eigenvalues, lambda 1 through lambda n. And under this inner product, these eigenvectors turned out to be orthonormal. Okay, and that was quite convenient in the sense that we could somehow, every time we wanted to understand what this operator does on either rows or columns, we could decompose it on the V1 component and everything else, and just deal with those two components separately. And okay, and the top eigenvector is basically the all ones function. And the corresponding eigenvalue was 1. And we sort of saw that all eigenvalues are between -1 and 1 anyway. And if you exclude the trivial eigenvalue, which is at 1, corresponding to the eigenvector, which is the all ones, you want to ask, can I put all the other eigenvalues within a smaller ball? And the radius of the ball is basically whatever is the two extremes. Like lambda 2 or lambda n are the two extremes. So whatever is the largest absolute value among these. Okay, and we called this lambda, and the spectral gap was basically 1 minus this lambda. That is, how do you have some gap between the trivial eigenvalue and every other eigenvalue? Okay, and there is also an equivalent way of looking at spectral gap again, which is in terms of what this matrix does to vectors orthogonal to the all ones vector, like how much does it shrink? Okay, and today we will sort of encounter fractions of this sort, which is often called spectral norms for matrices. So we'll encounter something like this, and we sort of saw that if you think of a random walk where you start with the distribution P0 and then you just let the distribution evolve as you take steps in the random walk. The evolution is given by this because it acts, you think of distributions as rows, and then this is the evolution that you have. And one of the things we notice that as I becomes larger and larger, you sort of get closer and closer to the stationary distribution. Okay, and how close you sort of have an exponential drop with respect to this lambda. Okay, and that's what we saw last time. And there is a root n thing that comes because of Cauchy-Schwarz based on whatever was the initial this thing. And just to recall, there is this, we define this notion of total variation distance. This is also sometimes called statistical distance. It's in some sense the most natural distance metric that you have between probability distributions. And we sort of saw that this particular distance metric, as I becomes larger and larger, it starts going to 0. As long as you're given a guarantee that this lambda is strictly smaller than 1. Okay. And last time we just saw a couple of examples where lambda is equal to 1. In the sense that either the graph is disconnected or the graph is bipartite. These are some bad cases. But if you ignore those, like lambda will be like bounded away from 1, and then this goes to 0. And usually the thing to keep in mind is this quantity. That is, if you want this to be at most some epsilon, whatever is your parameter epsilon, then these are the number of steps you need to take. So roughly like a log n divided by log 1 over lambda. So if lambda was a constant, this is like order log n or log n over epsilon. But if lambda is like 1 minus an inverse polynomial or something, then this becomes polynomial in the parameters. Okay, good. So before we do today's thing, I want to go back to this randomized algorithms that we were looking at, because this is going to be like the first application that we will see. And this is also where we started when we started looking at expanders. So let's sort of get back to this. So we have some language of interest. And this language is just a bunch of strings, and some of which you want to accept, some of which you want to reject. Maybe this language is a set of all numbers that encode a prime number or something of that sort. Okay, I'm going to be very loose here, but I'm just going to say a one-sided error randomized algorithm is an algorithm of the following type. Okay, so you think of some deterministic function A that takes your input X, but also takes some random bits. This R is supposed to indicate some random bits. And then for every choice of X comma R, it decides to either accept or reject. That's the way the algorithm A behaves. But what is the guarantee that I would like? I would like the guarantee that for every X, for every possible string X that you have, I want to say that if X is in the language, I don't want to make any error. And I'm going to say this by saying that if I think about A of X comma R as I vary R's, okay, somehow for every choice of R, I always return 1. So there are no bad choices of R with respect to things that are in the language. Okay, but when X is not in the language, ideally I would like to say that for every choice of R, I again say no. But maybe that's not the situation we have. But I at least want to say that the chance that I say yes mistakenly is not too large. It's like it's at most some half or something. Okay. So this is either RP or co-RP if you have seen it, but typically right now there's no time complexities that I have put here. But typically what you assume is that the length of this random bit as a function of the input X is not too large. So typically I'll be using the letter M to denote the length of this random string. And you assume that M is like some polynomial function of the length of X. Okay. And secondly, you also assume that this A is actually a polynomial diagonal. So that's the typical setup. Okay. So this is what you often deal with. And so this basically is an example of a one-sided error randomized algorithm where the error probability is like half. So the error probability is only in the no instances, and there's a probability half of error if I'm choosing R. Okay. So the first thing I want to ask is like, okay, maybe you're not satisfied with error being some. You want the error to be some delta. You have a particular delta in mind, maybe 0.0001 or something. But all I have is an algorithm with the above guarantee. And I want to know, okay, what do I do if to take this algorithm and modify this algorithm in such a way that I now have a new algorithm where this guarantee where this half is replaced by delta. That's what I would like. Okay. And this is the obvious thing that you do, which is you just repeat the same algorithm many times. You know that, if the algorithm says no, even in one of those instances, you know for a fact the answer is no. Because your confusion is only if the algorithm is returning yes, because there was a small chance that even in the no cases it returns yes. So the obvious thing to try is just repeat this algorithm many times and reject if any of those runs ends up rejecting. Okay, so we'll denote this algorithm as whatever A power T or A with a superscript T to basically repeat the algorithm T times, and you accept only if all of them end up accepting. Okay, and I just want to get a sense of, what is the guarantees that this algorithm has. Okay, so let's first ask the following question. Suppose I gave it an input X which was in L. Okay, what can I say about this algorithm? Notice that the probability that this AT on X with random bits, whatever, R1 through RT, because it needs to run T runs, so it needs fresh randomness for all of the T runs. This is equal to 1 so this is basically going to run A on X comma R1, then A on X comma R2, etc. So therefore, this actually is going to be 1 with probability 1. Because every single run, you know for a fact that your previous algorithm A is going to output things. So therefore, no error here. Okay. What about if X was not in L? Then the probability that AT of X comma R1 through RT, this is equal to 1. This is the same thing as I ran T independent runs of the algorithm and I'm accepting only if all of them accept. So this is going to be probability of A with X comma R equal to 1, but raised to the power T. Because they're T independent runs and therefore the probability just splits into a product. And I know that because X was not in L, this is at most, whatever, what did we assume? It was half. This was at most half. So therefore, what you have here is like, this is going to be 1 over 2 power. Okay, it's a very simple thing that you want to do. And the key takeaway is just the following. So that is, if you want to, did I say epsilon or delta? I said delta. Okay. So if I want to get this less than, if I want to make this quantity at most delta, then note that I need to set T to be equal to something like log 1 over delta. Okay, so that's the number of iterations that you need to run in order to get the necessary thing. Okay, so let's get a sense of this. So if my goal was to get to error delta, that is my goal. My guarantee of the initial algorithm is just error half. I want to know how many different runs do I have to try and how much random bits am I using overall. So the number of runs we just saw, this T is just order log 1 over delta. And how many random bits are we using? Every run involved m random bits, and I'm running it T times. So it's going to be T times whatever is the random bits required for each run. So it's like log 1 over delta times. Okay. If you solved problem set 1 question, the same question we ask, instead of asking independent random bits, what happens if we choose a pairwise independent random bit? And there we would have gotten, this looks like 1 over delta, and this looks like m plus log 1 over delta in that case. Or 1 over delta. No, is it 1 over delta or 1 over delta squared? Something. It was poly in 1 over delta rather than log. Whereas the number of random bits became a sum rather than m times log 1 over delta. That was the gain that you had, but the loss that we had was that we had to run a lot more tries. Okay. So if you think about randomized algorithms, the number of tries is going to basically dominate how much time your new algorithm takes, because you're going to get a factor T over that. So you don't want T to be very large. And this is going to sort of give you a sense of how much more random bits did you need in comparison to what you started off with. Okay. And by the end of today's class, we'll sort of see that you can actually improve this significantly. All right. So it's good to have this following pictorial thing in mind. So let's say this is the picture of all random strings or all R's, all candidate R's. Okay. Let's fix an input X. Okay. Now, if of course X is in L, then the algorithm is not making any mistakes. So there's no problem. The problem is if X is not in L, then there is some set of random strings that make your algorithm wrongly think that the X is in L. Okay, I'm going to just, as a cartoon, just put this set B. So B is equal to the set of all R, such that A of X comma R actually returns 1, even though X is not in the language. And what we have right now is that the guarantee is that the size of B is at most half times 2 power n, if m is the length of the random string that we have. Okay. And previously, what were we doing? We were saying that I want to choose a new algorithm. So this new algorithm is going to sample a bunch of points like this and hope that one of these T points fall inside this bad set P. Or sorry, one of these T points fall outside this bad set. You want to say that the chance that all T of them lie inside this bad set is quite small. The pairwise independent way of doing it was again saying, like, instead of picking these T points at random, you pick these T points in some pairwise independent fashion and somehow show that, you know, the chance that all of them fall inside B is smallish. Okay, so like So this is like an easier version of samplers. Typically for samplers, you're trying to estimate the size of B. Whereas this is more like you don't want to be locked inside. So this is in the one-sided error algorithms, I mean, that's what you're trying to, you want to make sure that you hit something outside of B, like you're not stuck in B all the time. Okay, so this is the picture that I would like you to keep in mind. We'll revisit this by the end of the lecture. But now let's move on to the setup that we had. We had an expander graph. We were dealing with expanders, and we were told that we have a bunch of these eigenvectors that are nicely orthogonal with respect to some inner product. Okay. Now, you may have seen in other contexts that whenever you have an orthonormal decomposition as a bunch of eigenvectors, you can sort of diagonalize your matrix. Okay. The standard way to do this is like if you have a bunch of eigenvectors, which is v1 through vn, which are orthonormal, you can write your matrix as summation lambda I vi transpose. You can write it as a sum of rank 1 matrices. Here, the dot product is a little weird. So one needs to be a little careful about exactly what happens. But I want to sort of make this following claim. That the matrix M has the following property, which is that it is equal to, if v1 through vn are the eigenvectors and lambda 1 through lambda n are the corresponding eigenvalues, and the dot product is with respect to this stationary distribution pi, then what you have is this. I was hoping to, okay, let me just do this. I thought I had erased all of this. Yeah, okay, so, and we are going to, so this is going to be some sort of, it's like the rank 1 representation of the matrix, okay, and I basically want to, it suffices for me to show that this left hand side and the right hand side are the same. I will just show that its action on every Vj is the same. That would automatically imply that the two matrices on either side must be the same. Okay. Now, the left hand side, if I act on Vj, I'm going to get some MVj. I don't know what this is. But let's look at the right hand side. What is this going to be? This is going to be a sum over I, lambda I times Vi transpose pi, and then now I need to put Vj. And we already know what this is. This is lambda I times Vi times, this is the inner product of Vi and Vj under the pi naught. Okay, because the inner product was basically the first vector transpose times pi times the second vector. Okay, and we know that Vi's and Vj's, they are orthonormal. So therefore, if I was equal to j, then this is 1. But if I was not equal to j, this is 0. So the only term that survives is actually equal to lambda j Vj. The only term that survives is the j I equal to j term. And that's also what this is supposed to be. Because Vj was the eigenvector for M. And so this tells you that the left hand side and the right hand side matches for all these things. So therefore, this is the same. Okay.
Pi you're interpreting as a.
So yeah, this pi is a diagonal matrix where you put the whatever the stationary distributions. That's what the diagonal matrix is. I mean, in a traditional fashion, I mean, if you're dealing with a d-regular graph, this pi is the 1 over n times identity. Okay, so it's actually, so let's focus on what will this matrix look like. So the first, so obviously, whenever we were dealing with it, we were somehow handling V1 separately. We were sort of dealing with what V1 does separately, and then the rest of the stuff. And somehow the rest of the stuff was getting dampened by lambda or whatever. So let's just get a sense of what is this matrix V1 transpose pi. In this case, V1 was the all ones vector. Okay, so can someone tell me what this matrix will be?
Pi is identity.
I'm not assuming pi is identity. I'm saying pi is an arbitrary, I'm just putting a stationary distribution on the diagonal.
So the sum of the diagonals can be this thing.
Not quite.
Matrix.
So this is a matrix. So this is going to be some n cross n matrix. What is this going to be? So okay, for the moment, let's just ignore this pi for. If it was 1 transpose, this is basically the all ones matrix. matrix which is completely contained of all ones. Putting a matrix on the right, especially a diagonal matrix, is like you're doing some column operations. And a diagonal matrix is like scaling those corresponding columns. Okay. So in fact, what this matrix is going to turn out to be is just a matrix where it just has pi's written down as each row. Like each of the rows will just be pi. Okay. And I'm going to refer to this as M_int to sort of, this is like the analog of the complete graph when it comes to the, the T regular thing. Something where no matter what vector you give it, whatever probability distribution you give, it's just going to spit the stationary distribution. That's it. It doesn't care about this. So think of, because this is something that sort of the only thing it retains is the component along V1. Everything else it just kills. So if you think of what it does on probability vectors, the stationary distribution will stay as the stationary distribution, but anything orthogonal to the stationary distribution will be set to 0. It just completely kills it. Okay.
No, so that was for that. Why did this? Why did you have to go to that was on this side?
Yeah, because it's a rank 1 matrix. So there's one vector that it will retain, everything else it will kill. No, it's just I'm trying to say that this is like the complete graph. Because a complete graph is one thing where no matter what distribution you start off with, in one step you mix completely. This is the analog of that, except you need to mix in the sense that you need to end up with the stationary distribution. So it's just a hack to somehow make that look like that. But it's convenient to think of the case when if G is deregular, then this pi is basically 1 over n times the identity matrix. In which case, this is basically the matrix that's made up of 1 over n everywhere. Okay, and sometimes this matrix is called J. Usually when people consider random walks, it's called the J matrix. The only thing it does is it takes a vector and it just replaces every entry by its average. So if you think of its operation on row vectors, column vectors, that's sort of what it looks like.
What did the subscript mean?
So it's like as if you're taking a completely independent next vertex.
Okay.
Rather than you taking a walk in the sense that you're at a current vertex, you choose something locally around you. You just forget about what you are in and you just sample one according to the station distribution pi and then go to the new vertex. So that's like the complete graph. Okay. Good. So now, before we move on, so there is something that is going to turn out to be very useful, which is this notion, there's a norm which is called the spectral norm. Okay. Because this is often what you end up studying when you are trying to deal with the linear algebra of random walks. And the spectral norm is usually defined with respect to some inner product. So you could, the norm that we have here could be with respect to the pi inner product or whatever you care about. I mean, it might still make sense. And it just says the following: look at all possible vectors. How much does M shrink those vectors in comparison to its original length? That's what the spectral norm is. Okay, and this is a norm you can define for any matrix. This matrix doesn't need to have eigenvalues or eigenvectors or anything. This is something that you can just define for any matrix. Okay.
Equal to 0.
Sorry? Oh, yeah. Max over x not equal to 0. Yeah.
Here we don't care about being orthogonal to the
So far when we were dealing with spectral expansion, etc., we were looking at just the matrix's component on what it does on the orthogonal component and looking at the spectral norm just there. Like somehow ignoring the fact that, yeah, at all ones, you're not doing anything. You're not shrinking it at all. But if I ignore that direction and focus on the orthogonal direction, we're looking at the spectral norm. That's what we were doing. But now it's just going to be convenient to work with this as a general definition. It's going to be very useful to do this. And just to justify the fact that it is a norm, just look at the definition and notice that these properties just fall out for free. Like if alpha is a scalar, then the norm of alpha A is going to be alpha times the norm of A. Okay, mod alpha times the norm of A. Okay, and of course it is subadditive and it is submultiplicative. It's like a triangle inequality, and this is like you shrink and then you shrink again. So obviously the total shrinkage is going to be size of A, norm of A times norm of B.
So, vector norm it's an operator norm, and it's defined for any.
It's defined for any matrix and
any norm on the space.
Any norm on the space. It's sometimes when you're dealing with it, the way you should think of spectral norm is it roughly is capturing what's your largest eigenvalue. Okay, but of course, matrices need not have eigenvalues or something. So the right way to look at it is something called singular values. But ignore that for now. But intuitively, the way you should think of spectral norm is you're trying to capture what's the largest eigenvalue. Okay, good. And now comes what I wanted to. This is the whatever subheading we had for this lecture, which is a really, really useful fact to have in mind. It's just very convenient to work with this. So suppose you have some undirected graph G, and the stationary distribution, the relevant stationary distribution is pi. Whenever I mean stationary, I mean this, the one that is proportional to the degrees. Okay. Then turns out whether or not G is a gamma spectral expander is exactly a question of whether your matrix admits a certain kind of a decomposition. So it says that G is a spectral expander if and only if your random walk matrix that you had can be decomposed in the following form. There was the independent matrix we just wrote above, which is the one where each row is just pi, which is like the analog of the complete graph. And it says that it's gamma times this independent matrix plus 1 minus gamma times some matrix E. And the guarantee you have from E is that the spectral norm is at most 1. So you should be thinking of E as an operator that doesn't mess things up too much, in the sense that it doesn't make things worse. Like it doesn't stretch any vector. So it's like saying that the random walk matrix of the graph that you currently have with you is like, there's a gamma part of like an independent step that you're taking, plus 1 minus gamma of something that you're not messing up too much. Okay, and this, we'll think of this as the error term. And many times when you're trying to calculate something in the spectral graph theory stuff, your main term will sort of come from here. And this is basically your source of your intuition. Whenever you see an expander, you will say, okay, let's just imagine what would happen if things were completely random. So that intuition will really come from the contribution of the first term in whatever you're doing. Okay, and the error term is really whatever is the second term, like the worst case thing of the second term. Okay, and it's a very convenient decomposition to have, and we will use this in this lecture and also in subsequent lectures when we are constructing expanders in the next lecture. Okay, so I just want to, before I go into the proof of it, I want to make sure that the statement is clear. Okay, so this is giving an if and only if statement of whether or not your graph like corresponds to some gamma spectral expander. Okay. Okay, good. So let's try to prove it. The proof is actually not hard. In fact, we have been seeing this. We were doing it on vectors, and now we just need to think of it from just matrices. Okay. So let's first try to do the first part. This direction is in some sense the easier direction. That is, I want to assume that M has this decomposition. And from that, I want to somehow conclude that, oh, M must have been a spectral expander. Okay, that is, what do we need to show? We need to show that whenever I pick up a vector that is orthogonal to all ones, M ends up shrinking it by a factor of 1 minus gamma or something.
That means you just apply it on a vector.
Yeah, that's it. So this part is just completely trivial. So what is MV going to be? So fix any V that is perpendicular to the all ones. Okay, and I want to know what is MV. This is going to be gamma times M in V plus 1 minus gamma times EV. Okay, and we set up M in such a way that any vector that was orthogonal to the all ones vector, it just kills it. Because the only component it retains is the component along the all ones, and this has no component along the all ones. So this, this is equal to 1 minus gamma times EV, because the first term is just 0. So therefore, what is the norm? The norm of MV is at most, so in fact, this is exactly equal to 1 minus gamma times the norm of EV, but we are told that E has spectral norm at most 1. So the norm of EV is at most the norm of V. So which is at most 1 minus gamma times the norm of V. And so this is exactly, so this is the same thing as whatever, lambda times norm of V, where usually gamma is like 1 minus lambda. So the first part is like completely trivial. Okay. So now let's prove the second part. Okay. The second part is one of these just do it sort of thing. So I'm going to write down this matrix Q, which is M minus gamma M int. Okay. This is going to correspond to this quantity. Okay. And the goal is to show that the Q spectral norm is at most 1 minus gamma. If you can do this, then whatever is this Q, if I remove that factor 1 minus gamma, it's something that has spectral norm 1. Okay. So this is what we have to show. Okay. And here note that it suffices to show that Q of 1 is at most 1 minus gamma times, sorry, if I look at the norm of these things, and for all V that is perpendicular to the all ones, Q of V is at most 1 minus gamma times length of V. This is just Pythagoras theorem. Basically, you are saying if it shrinks anything in the all ones direction by a factor of 1 minus gamma and anything in the perpendicular direction by 1 minus gamma, that should just hold for all vectors just by Pythagoras theorem. Right? So, and let's just look at these two. So, what is Q of all ones? So, this is going to be M of all ones minus gamma times M in of all ones. But M of all ones is nothing but all ones. M in of all ones is also all ones. So, this is just going to be 1 minus gamma times all ones. So, of course, the vector shrinks because in fact the direction also didn't change. Okay. Now let's do the second part. What is QV, where V is, suppose V was orthogonal to the all ones. So this is going to be MV minus gamma times M int of V. And M int of V is just 0. So this is nothing but MV. And we know from the spectral expansion of M that this length, if I put norms throughout, this is at most lambda times the norm of V, which is like 1 minus gamma times the norm. That's it. So this basically tells us that the if and only if statement that we wanted holds. So QV is nothing but M minus gamma M int applied on V. Okay, but M int on V is 0. Because V is, I'm assuming that V is like orthogonal to the all ones. So therefore, M int on V is just 0. So this is just MV. And if I know that G is a spectral expander, then I know that the norm of MV is like lambda smaller than the norm of V. So you get this. Is it okay so far? Good. So this is an ultra useful decomposition to have, and we will see one application of this now, which is called the hitting property of expanders. Okay, so this is the statement, and in fact we will see a more general statement in your problem set and so on. And typically this is again done for regular graphs, and the station distribution is just uniform, etc. But I am doing it for the more general setting. But if you feel like this is confusing, just mentally tell yourself that it's a regular graph and just don't worry about row versus column, etc. and things should work out. Okay, but here is the statement I want to show. So suppose I'm told that G is a gamma spectral expander, and let's say the station distribution is pi. Okay. Now, there is some set D, which is this bad set that I have in mind.
Station distribution is fine
In pi. Sorry, spatial distribution is pi.
pi.
Yeah. Okay. And I have some bad set. And let's say the volume of this bad set is mu. Again, this volume has to be calculated according to the spatial distribution. So it's like, if I pick an X according to the spatial distribution, what's the chance that I fall inside this B? I am told that this is some mu. You should be thinking of mu as something like half or something, some small constant. Okay. And now I want to do a random walk. Okay. And how am I going to do this random walk? I'm going to sample the first vertex according to the spatial distribution. Okay, that's how I sample V1. And now what I do is like I just keep going to a random neighbor. I go to a random neighbor from V1 and then go to V2 and then to V3, blah, blah. And let's say I find T vertices. So I am doing a T minus 1 step walk or something. I'm taking T minus 1 edges. Okay. And I'm interested in what is the chance that this entire walk is completely stuck inside this bad set. Okay. Now, if things were independent, okay, if I was doing things completely independent, like V2 is not expected to be adjacent to V1 at all. I just pick up a new vertex V2, I pick up a new vertex V3. This value should be mu power T. Right? And what this says is that it's roughly like that. So you should really think of it as the thing inside is like so there are multiple ways to write this. So the thing inside, let me write it as gamma plus mu minus gamma mu. Okay. And I tend to think of this as 1 minus gamma times mu plus gamma times 1. Okay. Think of it as some convex combination between mu and 1. And how much of mu, how close it is to mu versus gamma is like, versus 1 is a function of how good your gamma is. If your gamma is really, really good, that is like gamma.
If gamma is increasing, your boundary is getting worse.
Oh, sorry, then did I mess things up here?
I think it will lambda.
Oh, and maybe this is like lambda or something. Anyway, we'll figure out, we'll see what the proof is. But intuitively, the point I want to make is that it sort of behaves like as if you took you're not dealing with mu, but something a little larger than mu, but it decays exponentially in that larger quantity. Okay, so I don't exactly remember what this is. What was the previous one? That I'm sure I wrote it correctly. Yeah, whatever, we'll figure out.
Because if you take a bigger extended, you're getting a.
Yeah, so or I think if we write it in terms of lambda, what else is going to be? So this is going to be 1 minus lambda times mu plus 1 minus mu whole power T.
Yes, but now you're saying lambda is.
Instead of mu to the power T.
Yeah, instead of mu power T.
Yeah, but now you're saying as lambda becomes smaller, you get a watts power. Then I just take a.
The smaller the lambda, the closer you should be to mu to the T.
So for example, here if
lambda is becoming smaller, I can say this increasing that.
oh, so then I'm sure I messed something up here. So anyway, we'll see the proof. Sorry, let me just write this as something. Something whole power T.
Mu plus lambda.
Huh?
Mu plus lambda.
Yeah, mu plus lambda will work, but I think I want to get a better bound than mu plus lambda. Anyway, we'll see what we get. Okay, and it's actually a surprisingly, it might be a slightly longish proof, but there is nothing conceptually. Sorry, V1 through VT not in B. No. I want to say that what is the chance that this entire set is completely contained inside B? Okay, I mean, in some sense, if you think about the randomized algorithm setting, this is the bad scenario. Yeah. Okay. Good. Okay. So now what we are going to do is just basically try to express this linear algebraically, and then let linear algebra do most of the work for us. Okay. So as a warm-up, let's just get a sense of, I want to somehow express just the first thing linear algebraically. I pick a V1 according to the station distribution. So this V1 is sampled according to pi. And I want to know what is the chance that probability that V1 is increased. Okay. And I'm going to do this a little differently by defining a projection operator. Okay. So let's say these are the whatever rows or columns corresponding to the set B. So what it's going to do is the entries that are in that coordinates corresponding to that, I want to retain it as it is. The rest of it I want to set to 0. So this is like if I feed it some vector, all it does is it zeroes out everything outside of me. Okay. So then this can be written as sum over all x pi transpose p applied on x. Is this okay? So pi transpose p is nothing but pi was your original vector v1, which is the distribution according to v1. Okay, but what am I supposed to do? I'm only interested in those situations where I fall inside the set B. So I zero out things outside of B, things that didn't satisfy my event. And now I add up all the entries. I add up all the coordinates that I have and ask, that's the probability that my first vertex is inside B. Okay, and this can be written as summation pi of x p times all 1 at x. I'm just writing it differently so that I will then be able to write this as some linear algebraic form. So think of p times all ones, which is like saying you're adding. So how do I mean, this is like, it's easier. So what I want to say is just the following. I want to say this is the inner product of 1 and P1 according to the distribution pi. Okay, I think it's just, we just need to look at it and then notice that taking the inner product of all ones is like adding up all the entries. And all that P is doing is it's zeroing out the things that don't satisfy your event. And that exactly is going to be the probability that the first vertex happens to be in the set. Okay, good. So now let's ask the second question. What's the probability that both the first vertex and the second vertex are in the set B? Okay. So again, I'm going to just write down and we just need to convince ourselves that what I'm writing.
The second vertex is after you took.
Oh yeah. So second vertex is like I pick V1 according to pi, and V2 is a random neighbor of V1.
PGP1.
Yeah. So this is basically going to be, again, this will be pi transpose. It will turn out to be P. I think it's going to be PMP. This evaluated at x, and then you run over all possible x. Okay, so let's just parse the statement. Think of the pi transpose is your original distribution. The first P is going to zero out everything that the first vertex itself was not in the set P. So those cases are just zeroed out completely. And then I take one step of my random walk. Now I'm at a new vertex. Again, I need to check, is this new vertex inside P? And this P again zeroes out things where V2 didn't happen to be in P. Okay, but now I need to add up all the coordinates of this new vector, and that's what this sum over all x looks like. Okay, and this again can be succinctly written as the all ones vector with PMP of the all ones vector under the inner product. Okay, it's you just need to write this down, and it's not hard to convince yourself that what is happening is okay. I hope this is okay. And in general, if I take t steps of this random walk, okay, this is again going to be the all ones vector, and this is going to be p times mp to the power t minus 1 times the all one vector at pi. So far, so good. Okay, so one thing to keep in mind is that the observation, which is that p squared is equal to p, because it's a projection matrix. Obviously, so p squared is equal to p. So it might just be convenient to just put this bracket here. I mean, the difference between these two expressions is that there are a bunch of p's that bunch up together. You might have pm, pp, pm, and so pm, p, pm, p. So there are multiple p's that show up, but it doesn't make a difference. Okay, it's just going to, because it's just going to be convenient to deal with pmp as one matrix.
For p equals to 1, this does not agree with the previous.
Yeah, so which is why the bracket was outside. So let's say for t greater than 1. So if t is bigger than 1, then this always is fine. Okay, so this is what we have, and therefore what I need to get a sense of is what is this right hand side. Okay, I know what the matrix P is, I know what the matrix M is, and I just want to get a sense of, what is this quantity on the right hand side. Okay, we're going to slowly keep on making bounds that we can make, and then eventually get the bound that we want. So the first thing I'm going to make use of is that I'm going to replace both of these ones with just ones restricted to the set B. Okay, so the first claim is that this is nothing but 1B and PMP P minus 1 1B. I mean, can someone say why this is the case? Why is it okay for me to replace the 1 with just the ones restricted to B? That is, I'm just zeroing out everything outside.
If you don't start from B, the first P operator.
Yeah, the first thing notice that you apply is basically the P applied on 1B. So it anyway is going to zero out whatever was on the other columns. So as this dot product, as far as this dot product is concerned, if these two vectors had entries outside of B, they don't contribute to the dot product anyway. Okay, so the only things that contribute to the dot product are those coordinates that actually are inside the set B. Okay, and okay, so far so good. And this by Cauchy-Schwarz, this is at most the norm of 1B times the norm of PMP P minus 1 1B. This is just Cauchy-Schwarz. So far so good. Okay, so now let's do the easy things first. What can I say about the norm of 1B? If I were to take the square, then this is the inner product of 1B with itself. And we have done this many times. This is the same thing as the probability that if I pick an X according to the stationary distribution, what's the chance that it actually is in B? And this is what we set as mean. So therefore, if I remove the square that is here, so what I get is square root B. So one part of it is done. This we know is at most square root B. Okay, so now I need to focus on this quantity. Okay, and here I want to just say that this PMP the whole power P minus 1 times 1B, this is at most whatever is the spectral norm of PMP power T minus 1 times the norm of 1B. Because that's the definition of spectral norm. Spectral norm is trying to tell you what's the worst case stretch you could have amongst all possible vectors. 1B is one such vector. And you're asking how much can PMP actually end up stretching? Okay. And thanks to the way spectral norms, etc. work, I can sort of pull the exponent outside because the spectral norm of a product is the product of spectrum. So the task therefore boils down to the following. What is the spectral norm of PMP? Or rather, I shouldn't say what is the norm of norm PMP. What is the spectral norm of PMP? Okay. If we get a handle on this, then we know what to do. Okay, good. So here is where the matrix decomposition is going to help. So notice that PMP, I'm now going to decompose M. Okay, this is going to be P times gamma times M int plus 1 minus gamma times E. Okay, and this is therefore equal to gamma times P M in P plus 1 minus gamma times P E P. Okay, so if I care about the spectral norm, this is at most whatever is the spectral, I mean gamma times whatever is the spectral norm of this guy. Plus, what can I say about the spectral norm of PEP? What is the spectral norm of P, for instance? It's at most 1 because all it does is zeroes out some coordinates. But obviously, if your vector is completely supported on those coordinates, P doesn't do anything. So the spectral norm is actually 1. E spectral norm, you know, is at most 1. So the spectral norm of PEP is the product of the spectral norms. So therefore, that's at most 1. So this is like, I'm just going to replace this with 1 minus gamma. Whatever that is. Okay. So therefore, the problem now boils down to what is PM in P? What is the spectral norm of that? Okay. We want to know the spectral norm of that. It will actually be easier to just figure out what is this matrix and just get a sense of what the spectral norm is. So we do want to point out, look, the way we are doing it is we started off with an expander graph and then we did this linear algebraic statement. And we've somehow slowly wiggled our way into dealing with the complete graph somehow. So it's like eventually what seems to be happening is if you know what happens on a complete graph, you know up to one extra 1 minus gamma error that is happening, it's basically what happens on a complete graph. Okay. So what does M in P look like, going to look like? Let's write this down as a matrix. So P looks like this. Okay, and then there is M in, which is like pi's. And then there is again a P. So what is this matrix product going to be? What will it end up doing eventually? So again, it's always good to think of things on the left as row operations and things on the right as column operations.
All the rows and columns not in B.
Exactly. So the one on the right gets rid of all columns that are not in B. And then the one on the left gets rid of all rows that are not in B. Okay. So what you end up is the matrix that is just supported here, and it just has the whatever is the, I mean, the residual things that are the coordinates of pi, which are in P, those remain. Everything else is completely zeroed out. Okay. Now, can someone look at this matrix and tell me what the spectral norm of this matrix is going to be? Okay. Why is the spectral norm of this at most mu?
Stochastic matrix.
So it's essentially a stochastic matrix. If you basically, obviously, the coordinates outside of P don't matter because it's going to make them 0. So you should really just be thinking of the spectral norm of just whatever, this part of that matrix. And that is a matrix where every row sums up to some specific quantity. What is that quantity? You add up all the values in the stationary distribution corresponding to coordinates in B. Okay. So here I want to say the relevant rows sum to summation pi x, where I range over x in B. This is exactly the same thing as probability that x is in B if I draw x according to pi, and this we know is mu. So it will basically tell you that therefore the largest eigenvalue this matrix can have is actually going to be mu. In fact, that's the only eigenvalue it has. The rest of it are all zeros because it's a rank 1 matrix. Right? So there are other ways of also convincing yourself that the spectral norm is like mu. So therefore, it's this is just at least this was the easiest way I could think of. Okay. So therefore, this tells us that the spectral norm of P, M, and P is in fact exactly equal to B. And the vector that works for it is if you take the vector, all one's vector but supported on B, then it will shrink. I mean, basically the factor that you get is exactly going to be this. Okay. Now let's put everything together. So what does this say? We were interested in the norm of PMP. And what did we say above? The norm of PMP is gamma times whatever was this norm plus a 1 minus gamma. And we just discovered that this is like gamma. This is like mu. So therefore, that is at most gamma times mu plus 1 minus gamma. Okay. And how did this tie up eventually? We wanted to know what is the tth power of this. Well, the tth power of this is just the tth power of this quantity. Okay. And eventually we want to know what is the probability that V1 through Vt was completely locked inside the set B. That happened to be the norm of 1b squared. There were two factors of norm 1b that showed up. Like one of them was here and the other one was here. Okay. Once we applied Cauchy-Schwarz and this thing. So therefore, it's going to be the norm of 1b squared times whatever was the spectral norm of PMT whole power t. And what you get is basically mu times gamma mu plus 1 minus gamma. Okay, so maybe let's take a few moments to write this. So gamma mu plus 1 minus gamma. This is the same, I mean, just to make sure that we, Srijato's point, this is 1 minus lambda times mu plus lambda. So, which is the same thing as mu plus lambda plus minus lambda. Okay, I'm just writing equivalent quantities. I don't know which one is more insightful. Okay, this is the same thing as 1 minus. Actually, this is usually the thing that I find the most useful most of the time, because it really is telling you that mu is getting replaced by some convex combination of mu and 1. Okay, and depending on how good lambda is,
Lambda if it is 0, which is
if lambda is 0, then basically this is mu. And like if lambda is largish, then you have to increase the mu a little bit. The worse lambda gets, you get closer and closer to 1. But the point is, no matter what lambda you have, as long as it's away from 1, this quantity is certainly a quantity that is at most 1, because it's a convex combination between mu and 1. Okay, so the final probability looks like mu times this. In fact, this also looks very nice. The probability that the V1 was in the set B, that is mu. And it's like saying, what's the chance that the subsequent things are also in the set B? If they were independent, it would have been mu again for each of those things. Now it's saying it's not quite mu, but it's something a little different. Okay, so let me just briefly go over it, because this is the longest proof, but there aren't too many different things that are happening. Okay, so what did we really do? The first thing that we did was to express the event that we care about as some stupid inner product. Okay, this required some rearranging of terms so that it starts looking like an inner product. But sort of hopefully this intuitively sort of makes sense as to what is going on. Okay, so now what you're doing is we just wrote the probability that V1 through Vt was completely locked inside the set B as an inner product of the 1b vector and this matrix applied on the 1b vector. Okay, and then we did one Cauchy-Schwarz and reduced the problem to measuring what is the spectral norm of PMP. Okay, that's what we wanted to do. And we wanted to say that, okay, let's first try and get a sense of what is the spectral norm of the independent random walk. And hopefully the spectral norm of PMP is related to that. And we formalize this relation by basically using our matrix decomposition and writing the matrix PMP as something that is like analogous to the independent part plus an error term. And we basically just looked at the independent part, and the independent part is usually very instructive. I mean, like you can just write down what is going on, and you know exactly what the eigenvectors, etc. are. So therefore, we immediately got that the independent part was just going to be the spectral norm is just mu. And then you just put everything together and then you get something that looks like some convex combination of mu and some error. Okay, so are there any questions so far? I hope this is sort of clear. Good. So now let's revisit our randomized algorithms question. So we had a randomized algorithm that had error half, and we were thinking of doing this running the algorithm t times. Okay, and hoping that one of these t runs is falls outside this bad set. So as usual, so let's fix some input x. In fact, this is an input x that was not in L. And we have this set B, which I called bad. So let me call it bad of x. This was a set of all R that made me incorrectly think that that x was in the language. These are the set of bad random strings. Okay, and what did we know about bad? This divided by 2 power m, this is like at most half. Okay, that is the original guarantee on what this band is. And what were we doing previously? We were saying that I want to run this algorithm t times. And what are the t things that I'm going to run it on? I said, let's just pick t things uniformly at random and hope that at least one of them fall outside the set bad. And we said that the chance of this happening is like half power t. Now, there is an obvious thing that we can try. So, which is suppose G was an expander on 0, 1 to the n. Okay, with this, the degree of this expander is, let's say, a constant. Okay, now instead of picking t things independently, what I'm going to do is instead the following. I will pick v1 at random. By the way, it's a d-regular graph, and let's say this was a regular. So that the stationary distribution is actually truly the uniform distribution, etc. Okay, if it's a regular expander and it's d-regular, then instead of picking t things at random, here is an alternate thing you can do. Pick v1 uniformly at random and start a random walk from v1. Okay, so choose v1 blah 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 till vt via a random walk. Okay, and what did we just argue? We just argued that probability that all of these things end up being inside this set B. This is at most, I don't know, some mu hat power t, where mu hat was some constant. It was something between half and 1, but nevertheless it was some constant. Okay, and so if we want this to be at most delta, then I need t to be equal to basically order log 1 over delta. There are some things that I'm hiding here. It's a question of how close is this mu hat to 1 and so on. But intuitively, it's if the spectral expansion is some constant, this is some constant, that constant shows up here somehow. For now, let's ignore that because we don't really know the nice relation that we have.
There will be a trade-off between D and gamma, right?
Yeah, so we have not yet gone there. So that's why I'm at the moment I'm not doing it. But at least this gives you a candidate of saying that rather than choosing completely independent things, you can choose an expander random walk. So, okay. So now let's get a sense of how many tries do we have or other number of runs if I want to get the error down to some delta. We just saw that the number of runs we need to do is like log 1 over delta. Okay, and here is the important thing. How many random bits do we use? Obviously, I need to pick the first vertex. That takes m random bits. But from that point onwards, I need to do this random walk. So I need to choose t neighbors, like one at a time. Now, every neighbor, I have only d neighbors with me because it's a d regular graph. So in order to specify a neighbor, I just need to choose log d random bits per neighbor. Okay, so this is going to be this plus t times log d.
T minus one.
Yeah, t minus 1 times.
Doesn't matter.
Yeah. Okay. And since we were saying that d is also a constant, okay, so this is basically equal to m plus order log 1 over delta. Because t was log 1 over delta. And what you get here is like, instead of previously, if you had chosen things completely at random, we were making use of m times log 1 over delta random bits. And now somehow you are maintaining the same sort of number of runs. The number of runs there was log 1 over delta. Here is also log 1 over delta up to some constants. But the amount of randomness that we are using somehow went from m times log 1 over delta to m plus log 1 over delta. So this was the situation that we had when we did pairwise independent, where we were able to get something like this random bits, but we lost a lot here. But now this is telling you that no, you can actually get the best of both worlds. You can get the number of random bits to be like the pairwise independent thing, and the number of runs to actually be like the independent thing. Like, you know, you don't actually sort of compromise on the number of runs that you're doing at all. Okay, it's a rather powerful thing to do. Like whenever you are dealing with somehow independent runs, you can try to correlate the different runs by choosing a random one, because they sort of behave independently.
Sorry, I have a stupid question. So for the bound, we needed the starting thing to be random.
Yeah, we needed the starting thing to be random. Yeah. Okay, good. So you could naturally ask.
This could be completely done combined way, you know, like, I mean, without, so I mean, you need this. You need, I mean, if this was given a vertex expander, as
Yeah.
a vector expander, then the whole thing is very simple.
Yes, that's
But
right.
you already did this equivalence between vertex
Yeah, I did.
vectors with little loss. You can show.
That's true.
But
Yeah.
there is, I mean, the relationship between vertex expansion and spherical expansion is not that good.
Yeah, it's not. Yeah, yeah. But
You can never get vertex expansion more than you get from spherical expansion.
Yeah, but that's still okay.
But nevertheless, I mean, like at least conceptually, I mean, like that would have also. I mean, you sort of want to say the chance that you're locked inside a small set, you can't be locked inside for too long.
And also in vertex
And that's obvious when you have a vertex.
Exactly. Yeah.
and also in vertex expansion, it is limited, like only small sets expand.
Yeah. Yeah.
Rather than that, it will not expand.
Okay. So now that you have seen one-sided error randomized algorithms, you just be wondering, why can't I do the same thing for two-sided error? Okay, maybe there is error on either side. I want to do the same thing. So usually when you're dealing with randomized algorithm and you have two-sided error, what you normally do is you run many tries and take the majority. And how do you analyze this? You analyze this using Chernoff bound. You have some concentration bound that you have and you somehow analyze that. So natural question to ask is, even in expander random box, are there really this Chernoff-like box? Okay, and turns out there is. And you will see this in problem set 2, or if you want, actually, Vadan's manuscript actually has a full proof of this. Okay, so let's just parse this statement. This is often called expander Chernoff bound. Okay, let's just imagine that you have some function f on vertices that you care about. You can just think of f as maybe just an event. That is, some vertices it takes value 1, some vertices it takes value 0. Or maybe f is assigning a certain number and you care about the expected value of f or something. Whatever. I'm writing the most general form that was present in Vadan's notes. Okay. And it says the following. Suppose, so how would you normally estimate the average? You will sample t samples and take the empirical average and hope that your empirical average is sort of close to the actual average. You do the same thing here, except your t samples are not independent samples. You do a random walk of length t. That is, you sample V1 according to the spatial distribution and then keep choosing random neighbors. So that's your V1 through Vt. And now what's your empirical average? Well, you just add up the values of the f of Vi's and take its average. And I want to know how much does it deviate from μf, the correct average, that is a true average of f. Okay, and it says the probability that you deviate by more than epsilon plus lambda, where lambda is the spectral expansion, that has basically the same error decay as the standard Chernoff bound has. So in some sense, it says that depending on what your setting of lambda is, once the deviation that you can have more than lambda is exponentially small. Okay, there are also analogs of this where if you really insist that no, I don't want this lambda to show up here, there are alternate statements where this lambda ends up showing here. Some there also, but usually this is the more useful notion because oftentimes, I mean, once we see it in the next class, you will be able to tailor your lambda the way you want. So think of it something like if you want a deviation of at most epsilon, you choose your graph such that the lambda turns out to be like epsilon by 2. And then you ask for an epsilon by 2 deviation here or some such thing like that. So this in general is called expander Chernoff bound, and the proof is basically very similar to the proof that we saw for one-sided error, except you cook up your matrix in such a way that this exponential Markov nonsense happens. It's actually very, I mean, like once you see it, it's a very simple analysis.
Like you have to decompose e-ball and then.
Yeah, so that's sort of what you have to
We
do.
basically just mimic the proof of the Markov.
Yeah, you mimic the proof of the Chernoff bound, but using this linear algebra, at some point you will basically have to argue what is the spectral norm of this matrix. You use the same matrix decomposition, and you will have an independent part. And the independent part will be a true Chernoff, and there'll be some extra error. So it's a very clean proof. Okay, and we'll in problem set 2, we'll sort of break it up into small parts so that this is one of the questions you can solve. But as I mentioned, this thing is actually there in Madan's notes. In problem set 2, I'll try to give a different version of a different proof of this. Okay, so how much time? Okay, I have about 10 minutes. Okay, so just to get a sense of, I'm just going to assume this above bound. Okay, and let's basically ask ourselves, suppose I want this quantity to be at most delta. What should I choose T as? Okay, and because it looks so much like Chernoff bound, the T that you need to choose is once again 1 over epsilon squared log 1 over delta. Okay, except you need to account for this lambda gap also. But if you ignore that part, it's like 1 over epsilon squared log 1. So let's just ask the following. Someone gave you some randomized algorithm. It had some error. I don't know, maybe the error is 1/3. You're not satisfied with an error of 1/3. You want the error to be like 1 over 2 to the k. Okay, of your choice of k. So let's just compare what would we get had we done these independent tries versus pairwise independent tries versus expander tries. So if we did an independent try, then we would have to run it k times, basically. Because if the error was half, it will sort of go down exponentially. So it's like k times. And the number of random bits we'll end up using is k times n, because each time is independent. Whereas if you are using pairwise independent tries, if you think about it, you will have to roughly run it like order 2 to the k times. Okay. But the advantage is that the number of random bits you're using is just order k plus n. It's not k times n, it's like k plus n. You just need to instantiate it. These are things that you probably had in your problem set, the first problem set, where you'll have to work this. And now with expander walks, what you learn is that you can again do it in order k times, because the error bound sort of goes down exponentially in the number of tries. Maybe it's a different base of the exponent, but up to constants, it's going down exponentially. And the number of random bits actually looks like m plus order k. If you want k tries, the first thing you sample completely at random. And then for k different runs, I need to sample log d bits, and d is like a constant.
Does it ever matter that the constant in front of n is 1?
So for example, there is one, like a consequence of this is the following. I'm probably killing one of my problem set statements, but yeah. So for example, suppose you have a randomized algorithm that has an error of half, but you want to get inverse polynomial error. So this tells you that there is a way of coming up with a new algorithm that actually doesn't use a single additional random bit, but actually gets inverse polynomial error. Just because in that case, you would want to set k to be like log n, and you can afford to brute force over order log n bits. So it's one of these things where you aren't using additional random bits, you're just running for more time. But somehow your algorithm now has a much better guarantee. Okay, so that's one of the consequences that you have here. Okay, so something that Srijato had also mentioned is that now, because we are sort of saying that, oh, depending on how you want to use it, I want to tailor my lambda accordingly. This is we were just happily saying that we will choose a graph that has the right lambda, etc. So far, I haven't even shown you a single expander. Okay, and many of the constants that are showing up here is really whatever the degree of that expander was, right? Because when I'm choosing a random neighbor, I have to choose one of those d things. And so an important thing that we want to get a sense of is, suppose you care about a target lambda. Like you want an expander where the lambda is something 0.01 or something. Okay. And in addition, you also want to construct really, really explicit expanders, because notice that in all of the applications that we were talking about, it's an expander on 0, 1 to the m. So it's on exponentially many vertices. Obviously, I'm not going to be able to write down this expander, but I want to be able to do random walks on it. That is, if I am at a certain vertex, I need some ability to say, what is my next vertex? Or can you tell me what my neighbors are? And I need to be able to do this without actually writing down the entire graph. This was similar to how hash functions, when we had this graph theoretic perspective on the samplers, etc. We were talking about, we would like the adjacency matrix to be really succinctly described. So that per vertex, I want to know locally what my neighborhood looks like. So we would like something like that. So that's what I mean by I want to construct really explicit expanders. And I want the lambda of that expander to be at most the target I care about. And I would ideally like my degree to also be some constant. Now, I mean, something has to give, right? I mean, like, I can't just hope for the target lambda and also say that I want the 3 regular graph that also has this property. So there's going to be some trade-off between what lambda you want and what degree you want. Okay, so the question that we are going to end up dealing with is, how large should D be if your goal is to get a lambda, lambda as your target? Okay, and it so turns out that this D has to be something like 1 over lambda squared. Okay, in fact, there are specific constants that you can pin down here, but I'm going to be loose about it. And so in general, if you want a target lambda, well, you should tell yourself that I need to actually account for a degree being like 1 over lambda squared. But fortunately, if lambda is some constant like 0.1, D is also some constant. I don't know, 10,000 or something like that. Okay. So what we are going to do in the next class is basically start building these expanders, because so far we have seen applications if there were a super explicit expander, etc. So from the next class onwards, we'll slowly build these expanders with the target that we care about. And the way we will do it is a really nice way of doing it, which is I will first give you some examples of base expanders. Okay, some graphs that have some expansion. Okay, and typically many of these graphs, in many reasons, or in many situations, these base graphs are often good enough. Okay, but these are graphs often based on some number theoretic results and other things. But we will also deal with some base graphs that we can analyze completely, and so on. So we'll start with those base graphs, but obviously this base graph will not have the property you care about. It will be a graph on maybe, 81 vertices with some degree or whatever. But eventually what you will want is you want a graph on many, many vertices while the degree stays small and your lambda being pushed to whatever you want to. Okay. So what we will do is we will look at something called graph operations. That is, you start with a graph and then you do operations on the graph that sort of changes these parameters in some way. Maybe there are some operations that increase the number of vertices. Maybe there are some operations that reduce the lambda. maybe there are some operations that reduce the degree. And we will eventually put all of these together to get a family of graphs that have constant degree and the target lambda you care about. Okay, so that's going to be the agenda for the next couple of lectures. And once we do that, all the applications that we were talking about actually become realizable, because everything that we were saying was conditioned on the fact that there are these explicit expanders, and we will now see that there are explicit. Okay, so are there any questions? Okay, cool. So basically from next time onwards, we'll start dealing only with deregular graphs, because the constructions that we're going to have they will maintain regularity. So next class onwards, I'll just stick with deregular graphs, etc., and we'll slowly go over these graph operations.